Okay, hello, welcome to another video on maths. Today we're going to be looking at compound angle formula and finding out what they are and where they come from. And the reason for that is arguably because knowing where they come from is a more interesting question, but also because I quote from the exam board, students must understand geometrical proofs of these formulae. So therefore, we're going to be looking at the geometrical proof of the compound angle formulae. Okay, to get things going, what even are we trying to find here? We're trying to find identities for sine of a plus b, cos of a plus b, and tan of a plus b, where a and b are two angles. And of course, it's worth mentioning what we already know is that sine, cos, and tan, they're not just numbers, they are functions, and therefore we're not allowed to just multiply out the brackets to find out what these expressions are. It's a bit more complicated than that. So, to help us, what we're going to be doing is we're going to be using this diagram here, which is, as you can see, we've got a right-angled triangle OQR with an angle of B. We've got another right-angled triangle OQP with an angle of A. And then just to finish off this sort of rectangular shape, in fact, it's not sort of a rectangular shape, it is a rectangular shape. We've got this right-angled triangle RSQ. With a currently mystery angle, which we're going to have to find. Okay, now technically, this diagram is enough information to need to be able to go away and find out what these identities are. However, that would be a little mean. But if you're feeling super brave, you could go away and start trying to play about with this diagram. But I'm going to, in this video, give hints and sort of tips along the way, pointers, so you know what you're sort of meant to be doing to keep on track towards finding the proof of these formulae. So the very first hint that I'm going to give you, just to make life easier, is we're going to make the hypotenuse of this triangle here 1. And that's just to make our life easier. The proof will still work even if we made that number something other than 1, but it does just make it easier if it's the number 1. The proofs would still work with a number other than 1 just because the trigonometrical functions sine, cos, and tan are just ratios. So if all the sides, for instance, on this triangle here were all double the size, the trig ratio would still remain the same. So that's the first tip I have for you. And again, if you are feeling brave, you'd be welcome to go away and have a go at it from here. But another important thing I would like to mention is that all the sort of stages to this proof, they're all going to be in terms of A or B. We're all going to be dealing with algebra here today. Okay, tip number 1. The first thing you need to do is you need to find expression for this mystery angle up here, RQS, so this angle here. Now, I am going to give a hint in approximately 10 seconds, so if you don't want the hint, want to have a go now, which you can, pause the video. But if you would like a hint, my hint would be you would have a go at finding this angle here first. That will help you find the angle up here. So find the angle OQP, and that will eventually help you find the angle RQS. So pause the video here, have a go at finding the angles mentioned, and I will come back to you in a bit and show you what the answers are. Okay, let's go through it. So, as I said in my hint, it would be easier to find this angle here first. So to do that, we've got simply a right-angled triangle. We know the angles in the triangle add up to 180, so it's simply going to be 180, take away 90 for the right angle, and take away A to get us what simplifies to 90 minus A. So that's that angle there. And the reason that helps is because the angle we ultimately want to find is now lying on a straight line with another angle that we do know. In fact, another 2 angles we know. So therefore, to find that angle RQS up there, we just got to do 180 because the angle's on a straight line. Take away 90 minus A, take away 90. And doing the algebra there simplifies to just A. So therefore, we can go ahead and label that angle up there as A. Now, that's going to be very important and useful. The 90 minus A, we're not really going to be using that again in this proof, but the angle A being labelled up there that will be very useful indeed. So the next stage in trying to approach these proofs is to find the lengths of all these sides. So that's my next task that I'm going to be setting you. Have a go at finding all these lengths here. And all you're going to need to do that, have a go at some classic old school Socrator trigonometry. So have a go at that. And then I've got an extra little question there, question 3, which will then give you a pointer towards finding these identities. So there you go. Pause the video, and then I'll go through this stuff later. Have a go at finding these lengths. Okay then, so finding these lengths, starting off with RQ, we got this right angle triangle here. So as this side is the opposite to the angle B, it's going to be sine of the angle times the hypotenuse 1. So it's just going to be sine B. Similarly, OQ is going to be quite easy as well. It's going to be the cosine though, because it's the adjacent this time. Cosine of the angle times the hypotenuse, cos B. Then we've got another right angle triangle up here with angle A, so RS. This time the hypotenuse is a little more tricky. It's sine B rather than just 1, but therefore it's still not too bad, because you've got to do the hypotenuse times by the opposite of the angle to get this side up here. So that's going to be sine A times by sine B. This side is adjacent, so it's going to be cosine of A times the hypotenuse, so sine B cos A. Moving on to OP, that's this side at the bottom here. That's going to be the adjacent to this angle here, but the hypotenuse is cos B, so it's cos A cos B. And then lastly, we've got QP, and that's going to be the opposite, so it's sine of A times by cos of B. Last two take a tiny bit more thinking. RU, first of all, which is this side here. Now we could do some trigonometry to find this length, but even easier is we realize we've got a rectangle here, and therefore this side RU is the same as SP, and therefore to find RU it's just going to be this little length here plus this little length here, which means that in total RU will have a length of sine A cos B plus sine B cos A. Okay. OU. Now, OU is a chunk of the much bigger line OP, which we already have. We know that OP is cos A cos B, but that's got that little extra bit here from U to P that we don't want. But good news is, at the top of the rectangle, we already know that the length of that little length there, sine A sine B, so therefore OU is just going to simply be this entire length, take away this length we don't want here, so that's therefore cos A cos B minus sine A sine B. Brilliant. So what? Moving on to question 3, hence find expressions for sine of A plus B and cos of A plus B by considering the triangle ORU. ORU is this one here, which we have all 3 lengths for. We can just do some trigonometry. This got a total angle of A plus B, so in theory, this side here is just going to be the the sine of A plus B times by the hypotenuse 1. So therefore, sine of A plus B must be sine A cos B plus sine B cos A. And then similarly, this length at the bottom is in theory just the cosine, and I mean it this time, the cosine of the angle A plus B times by the hypotenuse of 1, which of course is, we've already found, cos A cos B minus sine A sine B. So therefore, we have 2 of our double angle formulae written there like that. So we've proven them. So that's where they come from. However, there was a third formulae I did write at the very beginning that we wanted to find, and that was tan of A plus B. But tan of A plus B, we already know tan is just sine of something over cos of that same thing. So therefore, tan of A plus B is equal to sine of A plus B, which we've written at the top of the fraction here, divided by cos of A plus B, and we've written the expression for that on the bottom of the fraction. Now this is a perfectly acceptable identity for tan of A plus B. However, maybe we want to write it in terms of tan. Maybe we want to make it look a bit simpler. So to do that, a little trick, we can divide the top and the bottom both by cos A cos B. Of course, we're allowed to do that with fractions because, going back to a more simple answer, if we took 6/8, we'd be allowed to simplify that to 3/4 by dividing the top and bottom by 2. But we are dividing by cos A, cos B to get this. So we do that. Then, of course, because we've got sort of a V scenario, we call it here at Collier's, we can then split those fractions up into more mini fractions like that. So we've got now a total of 4 mini fractions there. And those fractions can be simplified because you notice we've got a cos B, which is going to cancel out in the first one, but then sine A over cos A is just tan A. And then similarly in the second fraction over here, we've got a cos A that's cancelling out, and we've got sine B over cos B, which would be tan B. Third fraction here, really nice because everything's going to cancel out completely to leave us with just 1. And then in the last fraction, we've got sine A over cos A, which is tan A, times by sine B over cos B, which is tan B, leaving us with a final, more simple answer of being able to write tan of A plus B like this. Okay, that's good. We have all 3 of our compound angle formulae. That's where they come from. That's the proof of them. As I said, you do need to understand these proofs for the exam, but it's also good to know them anyway. But also, there is some last extra questions to ask, and that is, what is sine of A minus B, cos of A minus B, tan of A minus B? Now, you can just look in the formula booklet if you want to know what these are, because indeed all 6 of these formulae are all in the formula booklet. But if you really want a really massive, tricky challenge, you can actually prove these last 3 formula here by a very similar method to what we just used to prove the formulas up here. You just take the diagram we'd already used before, a little adjustment, we've changed the labeling of the 2 angles here and here, but you do a similar process of basically trying to find expressions for all these lengths here. Little tricky, more tricky though than the other proof, and that's why I'm not going to set it as a compulsory question. It's more of an extension challenge question, because you're going to need to be able to complete the proof, use a bit of simultaneous equations, some factorizing, and even some other trig identities that you already learned in the first year. But if you want a real challenge, then that is something you can have a go at, and I will create a video going through the proof of them as an optional extra thing to look at. Okay, thank you. Hopefully that is cleared up what the compound angle formula are and where do they come from, or in other words, why do they work. Brilliant. Thank you and goodbye.